In this lesson, we're going to look at two examples that use the derivative. Union membership as a percentage of the labor force can be modeled by the function given, where X is the number of years since 1900. Find the rate at which membership is changing in 1960. So the first thing that we need is to find the rate that membership is changing. When we have a function, the rate at which a function is changing is its derivative. So we're going to find the first derivative by taking the derivative of the function that we were given. Here I just used the power rule and I was able to find the derivative fairly easy. Now that I have the first derivative, I can find the rate at which membership is changing at a specific point. So if I'm looking at 1960, that means I'm looking at x equals 60. So the derivative at 60 is equal to negative 0.04. If union membership is represented as a percent, that means that the union membership is decreasing, since it's negative, at a rate of 4% per year. Another application of using the derivative is when we look at marginal analysis. So the cost and revenue functions for production of table saws are given below, where X is the number of saws that are produced. We want to find the marginal cost and the marginal revenue and interpret them. Evaluate values of the marginal revenue and interpret. Look for any break-even points and look at the regions of gain and loss. And then we're going to look at the profit, marginal profit, and again, interpreting the marginal profit for certain numbers of table saws. So let's first look at the marginal cost and the marginal revenue. Marginals, remember, is the study of the rate at which the cost or the revenue or the profit is changing. So when we had a linear function, we would just say, all right, the marginal cost or the marginal revenue is the slope of the linear function. It's the same idea here, but when I'm not given a linear function, if I need to find the slope at a point, I'm looking at the first derivative. So the marginal cost is 6 when my cost function is 7,200 plus 6x. So this is similar to an older problem where you're given a linear function and you just look at the slope of that function. Taking the first derivative gave us the same result. Marginal revenue, now that I have a quadratic equation here, again, I'm taking the first derivative. So now my marginal revenue isn't a specific number, it's actually a function. So what does this mean? Well, the cost is increasing at a rate of $6 per saw, and the revenue is increasing at a rate of 20 minus 0.0066x per saw. It may look weird at first to see the marginal revenue as a function, but once we start entering values into it, it'll be a little bit easier to interpret. So let's look at evaluating R prime of 1500 and R prime of 4500. So when 1500 table saws are produced, my marginal revenue here is 10.1. When 4500 table saws are produced, my marginal revenue is negative 9.7. So when I produce 1500 table saws, the change in revenue for any additional saws is going to be an increase of $10.10 per saw. But if I produce 4500 saws, my change in revenue for any additional saws is going to be a loss of $9.70 per saw. Don't forget that even though we are evaluating at a point, we're still looking at a rate of change when we are interpreting our derivatives. Let's graph the cost and the revenue, and I've given you a window, and determine any break-even points. Then let's also look at any regions of loss or gain. So the first thing that we need to do is go into y equals and enter our two functions in. Once we have our functions entered, we can go to the window key. Remember, this first set of braces represents the x values. whereas the second set of braces represents the Y values. Once we have our window entered, we can hit the graph key and see what this graph looks like. We expect our revenue to be a downward-facing parabola. We expect our cost to be a line. We see that there are two intersections, so that means there are 2 points where the cost and the revenue are equal. So we're going to go ahead and find those by doing second and then the trace key, option number 5, and then finding each of the individual break-even points. Once I have my break-even points, when we look at the graph, we know that wherever the cost graph is above the revenue graph, we're going to have a loss. And wherever the revenue graph is above the cost graph, we're going to have a gain. So we notice that between my 599 table saws and my 3,644 table saws, between those two break-even points, we're going to have a gain region. Anywhere else in my graph, I'm going to have a loss. So to interpret everything that we found using the calculator, the cost and the revenue are equal when we have 599 table saws or about 3,644 table saws produced. We see that there's a region of gain between x equals 599 and x equals 3644, and there are regions of loss elsewhere. So we saw in part C, when we found the marginal revenue for 1,500, that we had a gain. And when we looked at the marginal revenue at 4,500, we had a loss. And that's because we were outside of this region of gain when we were at 4,500 table saws. The last piece of this problem that we're going to look at is profit. So we're going to find the profit function, find the marginal profit, and then evaluate at those same two values of 1,500 table saws and 4,500 table saws. So profit, remember, is the revenue function minus the cost function. Remember, whenever we're trying to find our profit function, we want to simplify completely. So I'm going to distribute that negative and combine my like terms. I also write it in descending order. From here, we can find the marginal profit by taking the derivative of the profit function. So we get negative 0.0066x plus 14, which means that the profit's changing at a rate of negative 0.66x plus $14 per saw. Next, we're going to evaluate P prime of 1,500 and P prime of 4,500. We already know what to expect based on what we saw visually on our graph. We expect that when we have 1,500 table saws, our marginal profit should be a positive value. And when I have 4,500 table saws, because I'm outside that gain region, I should have a negative marginal profit. So when I have 1,500 table saws, I get 4.1. When I have 4,500 table saws, I have negative 15.7. So exactly what I expect seeing the graph. If 1,500 table saws are produced, the change in profit for any additional saws will be $4.10 per saw. But if I produce 4,500 table saws, the change in profit is going to be a loss of $15.70 per saw.